Last section of chapter 7, 7.5. We're talking about the side splitter theorem. And the side splitter theorem is kind of, it's an extension of something that we talked about already. So let's draw a picture here, and this is what the side splitter theorem is all about. It looks kind of like the one we used on our opener, and that's part of the reason that I put it up there. It's similar to what we're doing today. So there's our setup. We have a triangle and we have a segment that's parallel to the base. So then I'm going to label these side links, A, D, B, C, and I'm going to call this whole side X, and that whole side Y. The side splitter theorem tells us that a line parallel to one side of a triangle divides the sides proportionally. Now let's remember proportionally. What do we mean when we say proportionally? Do you remember? What have we been talking about? We've been talking about proportions for all the chapters. It has to do with fractions, and proportional means the fractions are equal. So we can say, if, as a reminder, the same ratio. So it divides the sides into the same ratio. So just a reminder, in chapter 7, our main technique, if we're not sure what to do, is write a proportion. That's our tool for chapter 7. So I'm going to write some of the ratios that we get from the side splitter theorem. The key is that this side is parallel to the base. So we're not going to write all of them. So some of the proportions we get out of the side splitter theorem, I could say A over B, this piece over this piece, equals D over C. What we do with the side splitter theorem is we match the corresponding pieces of our triangle. So I'm matching the top part over the bottom part, top part over the bottom part. I could say X over B equals Y over C. That whole side divided by this side, this piece, equals this whole side divided by this piece. I could say A over D, match these two up, equals B over C. It's another one we could use. Oh, A over D. Thank you. I wrote my D backwards. A over D. So I'm matching the top parts, making a ratio of the top parts and a ratio of the bottom parts. All of these would be the same. I could do X over Y. This whole side divided by this whole side equals, I don't know, B over C. The bottom over the bottom. Lots more that we could write, but depending on how the problem is set up, these are some of the proportions that we could use. And the key is that this segment is parallel to the base of the triangle. So I said this is a connection to something that we did in the past. Mid-segment. When we talked about the mid-segment, how did the base, if this were the mid-segment, how did the base compare to the mid-segment? If this was the mid-segment, how did the two lengths compare? 2 times, right? The mid-segment. The base was twice as long as the mid-segment. And what did the mid-segment do to the sides? Bisected, cut them in half. So our proportion for the mid-segment would be 1/2. So the mid-segment is a special case of the side splitter theorem where our ratio is 1/2 because this was right in the middle of the sides. So this is related to mid-segments also. That's mid-segment. This actually is why the mid-segment works out the way it does. All right, questions there? Okay, let's look at a couple of examples using side splitter. We'll do an easy one first. Our clue when we're setting up our problems that we're going to be talking about side splitter is we have a triangle and we have a segment that's parallel to one side. All right, we want to find x. So our technique, we're in chapter 7. What's the first thing we think? How are we going to solve this? Set up a proportion. So that should be the first thing we think. Set up a proportion. So how do we want to set it up? Lots of ways we could set it up. Anybody have an idea of how we would do it? Or how you want to do it? What do you think, Tor? 9 over 3 equals 6 over x. That one works fine. Top over the bottom, top over the bottom. Keep everything, match up everything in the same place. Write our proportions in the same way on both sides of the equal sign. We're set. And then solve a proportion, what do we do? Cross multiply. So I get 9x equals 18. So divide by 9 and x equals 2. Easy, right? Yeah? Let's look at a little more complicated example. So here's our setup for this one. This one we have to be a little more careful, but not too bad. 3, 4, 2, and x. And we want to find x again. Oh, and I forgot one thing. So we see those two parallel segments, we think side splitter. So our technique, we think we need to do what? Set up a proportion. So how are we going to do it on this side, or this problem? Anybody have an idea? We want to find x, so how about we make x one part of one of the ratios? So x over, what do we want to make a ratio with x with? 2, okay. Equals, here's where we have to be careful. X is the whole side of the triangle. So we need, if we make the same ratio over here, we need the whole side of the triangle. 7 over, and we matched up x with this piece. We're going to match up the whole side of this side with 3. X over 2 equals 7 over 3. We had to figure out, since we're thinking about the whole side of this triangle, this side of the triangle, this whole side is 7. And now we're set, right? 3x equals 14. Divide by 3, so x equals 14/3. If you plug that in your calculator, you get about 4.7. So what we need to do is make sure you're matching up when you write your proportions, that you make your ratios with the corresponding parts of the triangle. Since we used one, part of our fraction was the whole side of this triangle here, one part of the fraction on the other side needs to be the whole side of the other side of the triangle. All right, let me show you one more where we have to be even more careful. and then we'll talk about a corollary. All right, so there are parallel segments. That should be our clue. Side splitter, setting up a proportion. But this time I'm going to do 4, 2, 6, and x. And I'm going to say, don't do this. Four over 2 equals 6 over x. Can anybody see what the problem here is? Why we can't do that?
If 2 is smaller than what x would be?
It has to do with the 2 and the x and how they're related. So let me use a highlighter. When I compare the 4 and the 2, I'm comparing two sides of that triangle. When I'm comparing the 6 and the x, I'm comparing two sides of a trapezoid. I want to compare sides of triangles. So I need to compare sides of those two triangles. So how should I set this up? That's kind of the same as that. So let's think a little harder. What do you think? 10? Is that what you said? 10 over x, because that's the entire side of the red triangle, is 10. 10 over x equals, and what's going to be our other ratio? 4 over 2. There we go. So we're going to do this. And the reason we had to be careful here is because the sides that we were given were the bases of the triangle. If we go back here, for our side splitter theorem, all the ratios we set up here had to do with the sides of these triangles, not the bases. This one, because it had to do with the bases of these two triangles, we had to set it up this way. So we would say cross multiply 4x equals 20, divide by 4, so x equals 5. So that one's a tricky, little trickier. All right. Questions on that one? Okay. Let's talk about our corollary. Our side splitter corollary. And just a reminder, corollary just means that it's an extra theorem that we can figure out really easily. I think of them as bonus theorems. All right, so our picture for our corollary is we have two intersecting lines, and now we have 3 or more parallel lines. So those all are going to be parallel. So really what we're doing is taking this triangle and just dividing it with more parallel segments. So instead of just one, we're adding more in, and I'm going to label these, let's call this A, B, C, D, E, and F. What the corollary tells us is 3 or more parallel lines divide intersecting transversals, that's these two, and how are we going to guess these intersecting transversals are divided? Since we're in chapter 7, we just talked about the side splitter. They're going to be divided proportionally. So these two, this is the transversal. And this is a transversal. So all we're doing is what this does is gives us more pieces to make proportions out of. So again, sum of our proportions. I'm just going to match up corresponding sides. So A over D. I'm matching this to this. What could be another ratio that I could match with A over D? What do we think? B over E. Yes. How about A over C? What could I match up with A over C? D over F. Yes. How about B over E? What? C over F. And let's do one just a little more complicated. How about A plus B over C? So this whole segment divided by that segment. What do I match up with that? D plus E over F. Perfect. Those are some of the ones that we can match up. This just gives us more ways to write proportions. Lots more that we could write here. Just like the side splitter theorem, you just match up the corresponding pieces and write a proportion with those. Questions there? Okay, let's look at an example. So my picture, not drawn to scale, so I know I'll try to make it look like the way I label the sides, but sometimes, so this is, okay, make sure I do this right. I need to get bigger like that, and bigger like that. Okay, and I'm going to say all four of these are parallel. So I don't know, these are streets or something, and this is 40, 50, and 62.5. And this is X and Y. And we want to find X and Y. So with these two transversals, will they eventually intersect somewhere? Yeah, they either are parallel or they have to intersect. So this would be our side splitter corollary. All these are parallel, that's our clue. So what's our technique going to be here? What's our main technique in chapter 7? Proportion, write a proportion. So for X, what, oh, I forgot one thing. That's 80. Be tough to do the problem without that. So what proportion could we write for X? To solve for X?
40 over X.
40 over X equals 62.5 over 80. It's matching these two with those two. Now I cross multiply. 40 times 80 is 3200 equals 62.5x. Divide by 62.5. And if I do that, I get x equals 51.2. So there's 1. And then y. What proportion can we set up for y? Anybody have that one?
40 over 51.2 equals 50 over y.
40. Oh yeah, we could set that one up. 40 over 51.2, the one we just figured out, equals 50 over y. So we get 40y equals 51.2 times 50. And then we would divide by 40. I don't have that one calculated out. I can't do that one in my head. So y equals When I divide this out, I get 64. Anybody have their calculator out? What's 51.2 times 50? So 40y equals 20, this one? Oh, 2,560. Okay. So we divide that by 40, and that equals 64. So just to get our... Really the same problems as we did before. Set up a proportion, match up the corresponding sides, and you're set. All right, questions on that example? Okay, last theorem, and then we're done. Angle bisectors. So here's our setup for this kind of problem. Angle bisector, what does that tell us that's happening to that angle? Cut in half. So that means these two angles are congruent. I'm going to call this A, B, C, and D. An angle bisector of a triangle divides it into two triangles with proportional sides. So that's what our theorem tells us. So the two triangles we're looking at, I'll highlight them here. There's my red one, and there's my blue one. So there's my two triangles that the angle bisector divides the bigger triangle into, and the theorem tells us the sides are proportional. So I could say, what proportion then could I write for these two triangles? I'll start. A over B equals D over C. Perfect. I could also write A over D equals B over C. And if we look at these, we can see we get the same thing when we cross multiply. Here I get A times C. Here I get B times D. A times C. B times D. But we set them up, we end up with the same thing when we cross multiply. Just gives us another way to set up a proportion. And our clue is this angle bisector. Sides are divided, divides the triangle into two smaller triangles where the sides are proportional. All right, let's look at an example with that, and we will be done with chapter 7. Chapter 7 is always nice because there's really one technique that we use to solve our problems. So there's our clue as to how we're going to do this. All right, and the problem says find x.
Is that an A or a 9?
That is a 9. There we go. That look better? All right, so how are we going to set this one up? Angle bisector. So our two triangles are divided proportionally. If it helps you to separate them, highlight them. Draw some lines on them to show you what what triangles you're looking at. There are my two triangles. Uh-oh, what are we missing from that red triangle? We know this side and this side of the blue triangle. You know this side and what do we?
Just subtract 9 from 24.
Just subtract 9 from 24. 9 minus 24 equals 15. So that side is 15. So what's our proportion?
X over 9 equals 25 over 15.
X over 9 equals 25 over 15. Perfect. Cross multiply, so 25x equals 225. Whoops, 15x. Cross multiply this way equals 225. 9 times 15, or 9 times 25 is 225. Divide by 15. And x equals 15. Questions? Okay, chapter 7. If you don't know what to do, write a proportion. Quick recap of what we talked about in chapter 7, just so as you're going into the review. Section 1 was just about proportions, solving proportions, making ratios. Section 2 was when we talked about similar polygons. That's where we matched up the corresponding angles, and we made proportions, we made ratios out of the corresponding sides. Section 3 was about triangles. That's where we talked about angle, side, and side. And for similarity, our sides had to be proportional. And then we just talked about section 5. We skipped section 4. Talked about section 5 with the side splitter theorem. All it has to do with setting up proportions. Okay, our homework. 2 pieces today. This is our homework for section 7.5, and then our test review. Is page 483. All right, so that's our homework. We'll go over